This video gives an overview of ongoing work at the Universities of Surrey and East Anglia into automated video-to-text systems. During Phase 4, we have been looking at person independence. In this video, we will provide a summary of the entire process, along with preliminary subject-independent lip-reading results. The current lip-reading process for a subject comprises of a sequence of 3 main steps. We have now reached the point where the process is fully automated, requiring no user intervention. The process starts with the automated facial feature tracking, visual feature extraction, and finally the lip-reading process itself. The first step is to automatically track a set of relevant facial features, including the lips. Previous tracking approaches were based on linear predictors. While this resulted in very accurate tracking, independent of resolution, the approach was subject-dependent. This meant that manual markup was required for each new subject, and despite tracking accuracy, this was a limiting factor of the approach. Work into non-linear predictors using machine learning went some way to addressing this, providing better generalization across people. Recent developments in facial feature regression has resulted in an approach able to estimate the facial features of any subject without the need for a pre-tracking training phase. By training on tens of thousands of static images, estimation is now robust to varying illumination conditions, face poses, and expressions. This in turn can be used to track the features of any face in any environment. Here we can see it is relatively unaffected by camera shake and low resolution. The next step involves extracting the relevant features used by the lip-reading process. The visual features, called CSAM features, are a result of separating lip shape and texture information by computing an active appearance model, or AAM, before being dimensionality reduced and recombined. The video shows the original video and the resulting CSAM shape normalized texture information. Shown here is the largest mode of variation in the CSAM space, which accounts for different mouth shapes and textures. While recent work has been focused on challenging outdoor footage, for quantitative evaluation of person-independent recognition performance, we use the audio-visual RM dataset. This dataset consists of 20 subjects, captured in HD resolution, where each subject reads 200 phonetically balanced sentences. For these tests, we use a front view camera for all 20 subjects. Using the CSAM features, the system starts the lip-reading process using conventional HMM classifiers with Gaussian mixture models to model the speech output, firstly using monovisemes followed by trivisemes. The system then applies a cascade of feature processing techniques, starting with feature vector splicing, followed by linear discriminant analysis, a maximum likelihood linear transform, and finally a subject adaptive transform. Splicing takes a window of 7 frames, with 3 frames to the left and the right of the current frame, and passes this to the LDA and MLLT stages, which decorrelate the features and project them to an optimal subspace. SAT, which is a speaker adaptive transform, is applied to normalize the effects of variations across different subjects and is composed of FMLLR, splicing, and LDA. As will be seen, each stage of processing provides a performance increase. A deep neural network, or DNN, is attached to the end of the system. The DNN has been shown to further improve audio-speech recognition tasks. We have found similar benefits for visual speech, and for some tasks, the benefits can be quite large. In order to see the improvements obtained by the different components of the lip-reading process, we will first see the result of performing visual lip reading using only monovisemes. This results in a number of errors in the output recognition stream shown by the text.
What is the constellation's gross displacement in long tons? Show me all alerts. Show the Enterprise's home port.
An improvement can be seen when trivisemes are used. However, there are still errors.
What is the constellation's gross displacement in long tons? Show me all alerts. Show the Enterprise's home port.
Further improvement in the results are obtained when subject adaptation using FMLLR is used.
What is the constellation's gross displacement in long tons? Show me all alerts. Show the Enterprise's home port.
Finally, when deep neural networks are used, the results are significantly better when compared with the original monoviseme or triviseme approaches, as will be shown in the following sequences.
What is the constellation's gross displacement in long tons? Show me all alerts. Show the Enterprise's home port. Is England's remaining fuel insufficient to arrive in port at current speed? List Fox's average displacement and capabilities. Show the Gridley's track in bright orange with horns in dim red. Is Reeves's fuel capacity greater than Sterrett's? What if Flash's maximum speed were decreased by 5 knots? What's the Guardfish's ETA at Olympia?
What is the constellation's gross displacement in long tons? Show me all alerts. Show the Enterprise's home port. Is England's remaining fuel insufficient to arrive in port at current speed?
What is the constellation's gross displacement in long tons? Show me all alerts. Show the Enterprise's home port. Is England's remaining fuel insufficient to arrive in port at current speed? List Fox's average displacement and capabilities.
Is Jason's training rating greater than Jupiter's? Is Mercury's gross displacement less than that of Bainbridge? Of the Bainbridge, yeah. Is Mercury's gross displacement less than that of the Bainbridge? Is Prairie's economic speed greater than Reclaimer's?
Is Prairie's economic speed greater than Reclaimer's? Draw Dale's last 4 locations in the data window. Is Sherman's propulsion type the same as Tripoli's? Get the supplies readiness for Enterprise.
These figures show quantitative results for word error rate across the whole RM dataset. Each test is subject independent, by which we mean that the subject was not seen by the system during training. The figures show the performance increase at each stage of the pipeline. Here we see the individual performance for subjects. Again, the same trends can be seen.